Who's contributed here already?
I have.
I have. My name's on the list.
I'm in memos. You're in here too? I like to write them down too.
Go ahead, Myron, connect to it. You know how? The thing on Facebook, if you go to the Facebook page,
We're gonna be able to see this.
if you go to Facebook and you tap on the invitation, all that stuff's there. It should just pop up for you. I can't do it because it's the same stuff as this.
Facebook, when it's on these international dial numbers.
Hello?
Give me that right when I sit down. When you give me that when I was up there, huh? That's right. I take the money.
Hi. No, I'm trying to get this meeting started. I do. Love it.
Efforts to balance all things out that are thermal. There's a misconception that heat rises, and that's true as it pertains to fluids. Hot air, hot water will rise. They're less dense than their surroundings. Radiant energy travels omnidirectionally through the path of least resistance. And so if you've got a radiant floor heating system that has no insulation below the radiant floor heating system, you can expect significant back loss or back gain to the space below. It's usually a basement. We get those calls all the time of, hey, my main floor won't go above 65, but my basement is about 75. And we know immediately what the problem is. There's no insulation. So we recommend that they insulate those joist bays. It's now standard code requirement, did not used to be. A lot of systems don't have it. All right, so we've all experienced radiant heating. Basically, this is an infrared image of a radiant ceiling heating panel. It's very nice. I have radiant ceilings, radiant walls, radiant floors, and radiant windows in the houses that I own. And quite honestly, I like the radiant ceilings better than I do the radiant floors, only because I don't have to worry about what I put on the floor for floor finishing. I can cover it with bare rugs if I want to, and it does not affect the output of the radiant panel at all. I can also get more BTUs out of a ceiling than I can a floor. A floor is limited to 85 degrees Fahrenheit, and that's not a physical limitation, that's a human physiology limitation. If our skin's in contact with the surface greater than 85 degrees Fahrenheit, our body will break out into a sweat. So we've all experienced the opportunity of standing next to a dark brick wall in the evening that has been exposed to sunshine. You can feel the radiant energy pouring off of that. You have thousands of sensors on your body that can pick that up. You've also felt sitting in front of a campfire on a nice clear starlit night. Your surroundings are cold, but you can feel that radiant energy coming at you. And that's what this is all about. We address comfort, human comfort, through the use of radiant technology as opposed to convective technology, or a combination of both. But the one thing that drives the bus of human comfort is the mean radiant temperature within any given space. And the only way that you can affect the mean radiant temperature correctly is through the use of a radiant panel. And we've also walked into a radiantly heated home out of the cold, and it's like you're immediately enveloped in a blanket of comfort that is just fantastic. That's the reason that it has been around for so long, and why it is so popular is that it is extremely comfortable. And if you haven't experienced it, you need to. All right, so what dictates human comfort? Mean radiant temperature, MRT. It's the average temperature of those surfaces surrounding your body. That's the key factor to being able to maintain good human comfort. This is an infrared image of Robert Bean. If anybody knows Robert Bean, he's flashing himself to a panel radiator right there. Imagine that. Relative humidity. Relative humidity is, I'm sorry, the ambient air temperature is also very important for obvious reasons. And with a high mean radiant temperature, you can actually be more comfortable. I mentioned Robert Bean. Robert has a website called healthyheating.com. If you have any time on your hands, I would strongly recommend that you go there and check it out. It is the world's best resource for information pertaining to radiant and hydronics and home healthy home heating systems in general. And Robert has a calculator there that takes into consideration ambient temperature, relative humidity, and the mean radiant temperature. And you can change any one of those factors and see what effect it has. And he's got a cute little bunny. If the bunny's happy, he's pink. If he's cold, he's blue. If he's hot, he's red. And you can play games with those different factors and find out that you could have a very comfortable condition of 65 degrees Fahrenheit if you've got a higher MRT. So check that out and see what you think. Relative humidity. I'm sorry, any question?
What was that website again?
Healthyheating.com.
Healthyheating.com.
Yep. Relative humidity is also very important in maintaining comfort, and not just as a minimum. At a minimum, it should be at 30%. At a maximum, it should be around 50%. Seeing some interesting information coming around about the interface of humidity and the virus that's currently ravaging its way around the world. Humidity control is very important all the way around, not just the addition of, but also the subtraction of. Too much humidity in a lot of situations will cause you to feel uncomfortable. So it's important to control that. Another factor that's involved is noise. And some systems are more quieter than others. Hydronic, primarily, it can be extremely quiet, but it can also be extremely noisy. I've had systems where they've done staple up that when the tubing transitioned from 70 degrees Fahrenheit ambient temperature to the 140 operating, as it's expanding and it has a high coefficients of expansion, it sounded like a herd of crickets running through the floor. And having that much sound is not a portion of the comfort equation. So done right, it can be virtually silent. Done wrong, it can be extremely noisy. So a definition of comfort. A lot of people have different ones. I came up with this one based on my 45 years worth of experience. You're not too hot, you're not too cold, you're not over-humidified, you are not under-humidified, you're not hearing the delivery system in the background to any great degree. And simply stated, if all of this information is true, then basically you are truly comfortable. You're not thinking about it. And if you are thinking about any one of these factors, you're not comfortable. So what is radiant cooling? It's a process, basically the same thing, but whereby energy leaves the surface of a warm body and travels to the surface of another object and a cooler object. And it basically, again, in Mother Nature's efforts to balance all things cool, thermal. Here's a radiant cool ceiling panel that's put out by a company out of Italy called Masana. They're actually available here in the United States. They have a pretty substantial organization. They will do design engineering for your systems. They'll do the load calculations for you. They'll tell you what you need in the way of panels. It's impossible to carry 100% of the load with a panel only, so you need some other means of augmentation for being able to take care of the sensible as well as the latent energy, primarily the latent. You don't want the panels to take care of the latent, because if you do, you'll have moisture dripping off of the panel. We've all experienced radiant cooling, sitting outside again on a nice, cool, warm summer night with high ambient temperatures, but the sky is cloudless and clear. basically you're experiencing what's called night sky re-radiation. Outer space is at minus 327 degrees Fahrenheit. Heat flows from hot to cold. So basically your body is giving up heat to that minus 327 degrees Fahrenheit. And even though it may be 80 degrees ambient temperature, your body senses that energy that's leaving your body and going to outer space. So you feel the cool sensation. Walking down a frozen produce aisle at the local grocery store and feeling the coolness coming from the products that are in the freezers. You get a thermometer. The thermometer says the air temperature is 70, 72 degrees Fahrenheit, but that cold mass surrounding you is basically absorbing the heat off of your body and telling your body that you feel cooler than what the actual air temperature is showing. Air temperature is just one factor. Walking into a hockey arena, another prime example. The air temperature is 70 degrees, but that ice is pulling heat off of your body. Consequently, you can feel cooler. Now, the key advantage of hydronics over a forced air distribution system is pictured right here. Basically, this 3/4 inch tube right here, doesn't matter whether it's copper, PEX, steel, whatever you want, is going to transport the same amount of energy as this 8x14 duct. And conversely, a number 2 American wire gauge cable would also transport the same amount of energy that this 3/4 inch tube is, which is roughly about 40,000 BTUs. We want to limit our flow rates to these devices to around 4 GPM on 3/4 inch pipes. So parasitic energy consumption. Bear in mind, this presentation was put together by the Efficient Energy Building Association. And they were looking for means of being able to heat these super insulated homes with a reasonably priced comfort system. When you're dealing with a system that has a load of around 5 BTUs per square foot per hour, that's nothing. And essentially you're looking at a floor surface temperature of 72.5 degrees. So does it make sense to install a radiant floor heating system in a house that has a load of 5 BTUs per square foot per hour? Sure, the people will be extremely comfortable, but you've got to be careful what you promise. If they're expecting warm floors, they will never see warm floors ever. Any questions, Tom?
None yet.
All right. So basically we've got a system here on the left-hand side, which would be an air source heat pump that's around 3,000 watts per hour consumption. We've got fans that are going to move 500 to 650 watts per hour. And then we have a circulator that's going to move 25 watts. And this is going to move energy from this device into the building and essentially be much more efficient as far as watts per BTU of energy that's being moved. The capacity of air versus water. Air is going to carry 0.018 BTUs per cubic foot per degree Fahrenheit difference, whereas a cubic foot of water is going to move 62.4 BTUs per degree Fahrenheit difference. So water wins that bet every time. It's going to carry essentially 3,400 times as much energy as air does for the same volume and temperature differential. Here's a typical VRF distribution system. VRF is a variable refrigerant flow. Essentially, you've got an outdoor unit that can be either a compressor with a condenser or an evaporator. It's reversible. And essentially, you've got a manifold that distributes the energy to the units. You can have some units that are in heating and some units that are in cooling. This system is essentially something that is on the future. It's here today. The manufacturers of these come from the Far East, and they have made the claim that they will take over every methodology of heating in the world. And quite honestly, they probably could. They have a checkbook a lot bigger than any of the American hydronic manufacturers. They could probably buy the industry as a whole, just one company, Mitsubishi, as an example. Then we have radiant panel ceiling distribution systems. This is provided by H3, which is a division of Masana. And essentially the nice thing about a radiant ceiling heating system is that you do not have to cover every square foot of the ceiling in order to be able to deliver good radiant energy. And that comes from the fact that we're dealing with a higher allowable surface temperature on the ceiling than we would be with a radiant floor. And if you want to do this radiant ceiling system with, say, a solar thermal system, then yeah, you may have to cover every square foot. But if you have an alternative energy source like a boiler that can drive a higher supply water temperature, then essentially you only need to put in what's necessary to counter the load requirements for that given space. This is a typical situation where we've got an air source heat pump that's essentially the heat energy source itself, and it's going to distribute the system through a number of different methods. It could be radiant floors, walls, ceilings. It could be fan coil units. There's a whole bunch of different options that you have available for being able to generate conditions of comfort. Solar thermal. Solar thermal is very popular. An interesting fact that very few people realize is that solar PV at a peak is 20% efficient. And it starts degrading immediately from day one as soon as it's exposed to the sunshine, whereas a solar thermal system can be 60 to 80% efficient for the energy that falls onto the face of that panel. The biggest key factor is that a solar thermal system can basically stop the gas meter, but it cannot spin it backwards. Whereas the PV system not only stops the electric meter, it will spin it backwards. So for that reason, the DOE has decided that it's sexy and they've pushed that and promoted it. And unfortunately, the true leader in solar thermal conversion, which would be a flat plate solar collector and evacuated tube collector, has been pushed to the side because it can't spin the meter backwards. I really feel that that's an unfortunate situation. They also have combination solar and PV panels, which a lot of people are not aware of. But basically, by having the solar thermal portion in here, when it's set up correctly, it will actually enhance the operation of the PV panel because it keeps the PV panel cooler. Another technology that has been coming to the forefront in the last 20, 30 years is ground source heat pump. And ground source heat pump has a whole lot of different options. You can do a slinky pitch, you can do horizontal trench slinky, you could do vertical borehole. We've been tied into just about every system that's out there. With these ground source heat pump systems, if you're going to do a slinky pit, I would strongly recommend that you consider putting in a leaky pipe over the top of this whole system, because this is very dependent upon the moisture in the soil for its conductivity and its ability to be able to extract heat out of the ground. And when you get hit by a drought, there is no moisture. Consequently, your field goes dead. And then you have people that are complaining that their utility bills are high and that their comfort conditions are low. So that's something to bear in mind. If you're going to go horizontal, make sure that you have some means of being able to augment the soil and the moisture. Here's an interesting system. This is a thermal battery storage system, which is a group out of, I believe it is North Dakota or South Dakota. They're South Dakota. And essentially what they're doing is they take a large storage tank, and you can see the tubing that's actually a part of the heat exchanger that's built into this. And this is just basically water that's in this tank. And they use a water source heat pump to extract heat out of the water and pump that heat at 110 to 115 degrees Fahrenheit into the house for distribution through radiant floors, walls, ceilings, fan coil units, whatever. And people look at the storage tank and they go, why would you want ice? Okay, well, number one, 1 gallon of water, I'm sorry, 1 pound of water, 1 degree Fahrenheit difference between 32 and 33 degrees Fahrenheit. When it goes from 32 degree Fahrenheit water to 32 degree Fahrenheit ice, it requires 144 BTUs per pound. So this is a significant amount of energy that's available here. But more importantly, once this is frozen as a solid block of ice, anything with a temperature gradient greater than 32 degrees Fahrenheit becomes the energy source, which can include the outside air, an active solar panel. It could be a ground source heat pump. If you've got a vertical borehole well that you're running water into a house, that water is coming in at 40 degrees, so it's greater than 32, so it can help melt the ice. Snow melt system on a driveway, that's a huge solar collector. You can extract the heat off of that driveway and put it into this storage tank and remelt that ice and raise the storage tank temperature again. And I really feel that there's a huge future in the system. The most expensive component on a ground source heat pump system is the vertical boreholes. This is going to eliminate probably 75% of the required boreholes on a lot of systems. So watch for this to come to the forefront in the near future.
Mark, the ice making process is natural, outdoor, ambient.
No, we're extracting heat out of it with a water source heat pump.
Okay, so you're actually freezing that water.
Yes, intentionally.
Got it.
And then anything with a temperature greater than 32 degrees becomes the air source or the heat source for that storage tank to heat it back up. Solar panels, solar thermal panels have performance curves that are based on certain parameters, certain ambient conditions around the panel, solar gain, angle of the panel, etc. And it's based on a storage tank temperature of around 120 degrees. Well, if the storage tank were 32 degrees Fahrenheit, the performance factor for these flat plate solar collectors is off the chart. I mean, it's fantastic. So in speaking about how compatible hydronics is with alternative energies, basically simply stated, it's completely compatible with every alternative energy known to mankind, including those that haven't been invented yet. We have a lot of systems that we do here in the Denver metropolitan area. We have an incentive, a rate incentive, that the people that put solar PV onto their house get to bank the energy during the summer months that they produce that they're not using. And that's basically used as a credit as they're going forward during the winter months. So we've got a lot of customers that are converting from a gas forced air system to an electric resistance boiler based on the fact that they've got solar PV on their roof. Unfortunately, it's only 10% efficient, but the fact that they can spin their meter backwards is making it worth their while. So how long has hydronics and radiant been around? It's been around longer than me, and I've been around for a long time, 68 years. This is a picture from 1905 of a radiant floor heating installation being done. This guy right here is obviously the boss. This is a master plumber. This is the apprentice who's doing all the work. Thank God for apprentices.
What are they laying down there? I've run into old systems that they buried galvanized pipe or black pipe in the gravel.
Yep. This is actually copper that's going to be embedded directly into the concrete. And I'll tell you, copper has had a somewhat of a sordid history as it pertains to hydronic radiant floor heating problems. And the biggest problem is that the longer the tubing run is, the greater coefficients of expansion you have. If the tubing is completely encapsulated in concrete, it's still going to expand. But instead of doing it laterally, it does it nominally. So it basically compresses the tubing. And that continuous expansion and contraction of that tubing as it goes through heat cycle will eventually cause a fault, a crack in the pipe, and then you get failure. So the key to that is to keep your coefficients expansion to a minimum. So these guys are doing they could have been doing the runs this direction, the long ways. Personally, I would do that with PEX because I've got less time trying to do what this apprentice is doing, which is making the return bends. And the less time you spend on the bends, the faster you can put the tubing down. Well, if you do that with copper tubing, you're guaranteed that it's going to fail at an early rate. So by going at this shortest distance, yes, it's more labor intensive due to the return bends that you've got to incorporate into it, but it sees less of a potential for coefficients of expansion and subsequent failure. So the history of radiant panel systems, Roman bathhouse is probably the one that has been promoted the most. But in reality, there's actually some early ondol systems that came from Korea that were there even before the Roman bathhouse were. In 1907 was the first use of iron pipe in England. It was basically a steam heating system that was in the floor of some large greenhouses at a place called the Crystal Palace. And it was the first use of radiant floor heating systems, but it was actually steam driven. Frank Lloyd Wright was a radiant pioneer. He loved radiant floor heating systems. It gave him total flexibility in the design of his houses. He wasn't confined to not having to be able to put a couch in a given area because of the blocking of a duct. In the 1940s, copper and steel pipe systems were very popular. We still have a lot of functional copper and steel pipe systems. Ran into one the other day that was actually a steel pipe staple up. It was essentially steel pipe that was embedded into the tops of the floor joist, and then the flooring system was laid over the top of that. Works like a champ. There was no insulation below it, so it was an omnidirectional panel. You got both upflow and downflow of heat, but from the standpoint of comfort, it worked great. In the 60s, PEX was developed, which is a acronym for cross-linked polyethylene tubing. It was developed in Europe. And a lot of people wonder how long PEX has been around. Well, actually, the intercontinental cable that runs under the water between Europe and the United States is also encased in PEX. So talk about an acid test. It's been there. It's been there for a long time. And in 2015, I haven't had a chance to update these numbers, but at that point, there was 193 million lineal feet of tubing installed in North America. I can't tell you what went into radiant panels versus that went into potable water distribution systems, but I can tell you that that number has probably doubled since then. All right, let's talk about some of the advantages of radiant panel heating systems. It improves the comfort by increasing the average surface temperature surrounding human beings. That's what we call the mean radiant temperature. When it's properly controlled, it's very comfortable. When it's out of control, you find out what the true meaning of mean radiant temperature is. You get up to walk across the room to get a beer and you're already in a sweat before you get to the refrigerator. That's not comfort. It allows comfort at a lower or a higher air temperature if you're doing cooling. So typically in a properly installed, properly maintained and operated system, 68 degrees feels like 72 degrees. And I'm sure a lot of people have heard that, but you can also get into a situation where if they didn't take into consideration the mean radiant temperature of the glass and its proximity in relationship to the people, even though you've got a floor that's 85 degrees Fahrenheit, that glass is sucking the heat off of people's bodies so quick that they don't feel comfortable. So that you have to be careful about what you do there. And if you go to Robert Bean's website, he's actually a member of ASHRAE and was a key person in developing a program that essentially calculates what the mean radiant temperature will be for any given circumstance. And if you get into a situation where it's not going to be comfortable, it will tell you, and then you can tell the consumer, hey, you know, I can't guarantee your comfort because, and my recommendation would be that you go to triple pane windows instead of double pane so that we raise that surface temperature and lessen the possibility of you feeling uncomfortable. It provides an almost ideal match to the human thermal comfort requirements. And I'm sure anybody that has done this has probably seen the pictures that have come from about every major tubing manufacturer that shows the curve and what it is at the ceiling versus forced air versus radiant floors. And radiant absolutely comes about as close as you can get to the perfect comfort conditions. It reduces room air stratification and mechanically induced exfiltration. Those are pretty straightforward and obvious. So another key advantage is that many of the systems are out of sight, which gives interior decorators are just loving these systems. They have no limitations on where they can put furniture, couches, chairs, tables, whatever. However, we have to have control over what the finished floors are. And I guarantee you that every housewife has a tractor trailer rig full of Indian woven rugs that she hasn't told anybody about that are going to end up on that floor as soon as they move in. Been there, seen that. Easily zoned. I've had customers that have asked me to make every room an individual zone. He was a stockholder of Uponor, got all of his product basically at cost. And, you know, it's a fantastic system. I don't generally recommend that. I usually recommend a minimum of 3 zones. If they want to go 4, 5, 6, whatever they want, that's up to them. But typically common living areas, uncommon living areas, sleeping areas, and bathing areas. That's the big 4 at a minimum. There should be 4 zones. And I can't tell you how many developers get into these houses and start throwing radiant floors in thinking they're really going to cut a fat hog and they have 1 zone per floor. So if a consumer likes a cooler sleeping environment and you have sleeping and living spaces on the same floor, everything's got to be kept cool. Radiant systems are not conducive to deep setback and fast recovery. In fact, we recommend that you set it and forget it. If you're going to turn it up and down, make sure it's long-term. I'm going on vacation for 2 weeks, turn it down to 50 degrees. 2 days before you come back, have your neighbor turn it back up to 70 degrees, because if you don't, it's going to take it 2 days to make you comfortable again. Creates gentle room air circulation with a radiant floor and a radiant wall system. There is convective currents that will occur within that space. If it's a radiant ceiling system, unless you've got a ceiling fan, you can expect 0 convective current out of that system, which actually affects the net output of that radiant ceiling. Easily routed through buildings. It's a lot easier to run a 3/4 inch or a 1 inch or an 1.5 inch pipe through a floor joist than it is a 8 by 16 duct or a duct of any size. So systems with high thermal mass can respond quickly to increased loads necessary. This is the reason that radiant floor heating is popular in airplane hangars. They open those large doors up to the outside. They bring an airplane in, which has just come out of the sky that's very cold. As soon as they close the doors, boom, the temperatures back up immediately. That's because of the flywheel mass effect of the 12-inch thick slab that's got radiant tubing in it that basically is a large battery for being able to handle those changes. So systems with low thermal mass release heat almost instantly. This is where radiant ceilings come in handy. I have radiant ceilings at my house up in the mountains. I have an energy management system that I can dial up from anywhere in the world as long as I have internet access. And it is very quick in response because it's not having to heat 1.5 inches of concrete plus get through the pad and the carpet. It's basically a 1/2 inch of sheetrock that boom, the heat is into the room immediately. So that's definitely an advantage of a situation where you have an occasional use weekend cabin. Tom, put radiant ceilings in there, it's going to heat your house up pretty quickly.
What do you run the temperature in the ceilings, Mark?
I have mine running as high as 170 degrees, and it's kind of an experiment. Siegenthaler, John, is a good friend of mine and also a recipient of the Carlson Holothand Industry of Award of Excellence. And he said you should limit it to around 140 degrees because of the paper. And I'm like, screw the paper. I'm not worried about it. I want this thing to kick heat as quick as I can. So I've played with it. I kept bumping it up and up and up and up. I'm up to about 170 degrees now. When I'm accelerating, I'm at 170. Once I get up there, I limit it to about 140. I've got a fantastic energy management system that gives me options of occupied versus recovery, and I can tell my boiler what I want it to do based on input. I've got 3 inputs to it, so I can tell it what schedule I want to maintain. If I'm accelerating, I'll go to 170. Once I'm up there and it's stabilized, and I back it off to 140. So heated floors dry quickly. This is a sales point for people that are in a commercial business, a lumberyard as an example. You've got customers coming in during the winter months. It's cold outside. They work outside. They're going to track up to the counter to make an order. If you've got high density tubing in front of that counter, it does 2 things. Number one, it heats their feet, which makes them want to come back and buy more stuff from you. But more importantly, it dries the moisture off of the floor so that you lessen the chances of a slip fall hazard occurring in that space. Resistance to physical damage. I say this, and quite honestly, in the 45 years that I've been doing this, I've never seen a tube fail in the middle of a circuit without having a tradesman attached to a tool. The electrician discovered your heating line for you, or the sound guy discovered your heating line for you. I've never seen a tube fail. There's always somebody on the end of a drill or a hammer drill that basically found it for you. Can operate with virtually no noise if done right. If done wrong, it can be very noisy. Adaptable to any heat source or any fuel, propane, oil, wood gasification. I have a project that I did up in Washington State that is heated by geothermal. They literally drilled some wells down into the magma and dropped a 2-inch steel pipe into it for a heat exchanger. And they use that hot water to heat 200 small remote cabins throughout this whole process. And they're using old cast iron radiators, and it is very comfortable in all of these buildings. But I had a scary experience with it because we decided to flush the heat exchanger, and I asked them for a pump, and they brought me down a fire truck. And so we flushed the heat exchanger forward, got a ton of crap of rust and stuff out of it, and went to flip flop our hoses so that we could backwash it. And the lady engineer that I was working with was getting hot water poured on her. She's trying to switch her hose. And she said, would it be okay if I close this valve? And me not thinking, I'm like, sure, go ahead. She closed it. And basically that heat exchanger, water heated up and it hydro locked the ball valves. We could not open them. Do you know how hard it is to shut off Mother Nature? There's no disconnect switch. So I screamed, everybody away from the wellhead. They all backed away. I'm tapping on this valve, trying to get this ball valve to open up to release the static pressure, when a 2-inch cast iron T that was right at about face level exploded, basically popped from the hydrostatic energy. And fortunately, the water wasn't so hot that it caused me a lot of problems, but I got doused with some pretty hot water. And I said, why didn't you guys have a relief valve on here? Well, we didn't think about it. We didn't think we'd need one. We put one on. It's covered now. Reduces energy consumption. There have been study upon study upon study, and it depends on whose study you see. I've never seen a study that said radiant floor heating uses more energy than anything else. Number one, we got rid of exfiltration because of the fact that we're not moving air with a forced air fan. Therefore, we're significantly less air changes naturally occurring within the space per hour, and a higher degree of comfort. If you have rooms that you don't want to use, turn them down. If you've got rooms that you spend more time in, keep them set. So the reduction in energy consumption should be relatively obvious. So here's a quick case study. This is some of the simplest applications of hydronic radiant floor heating that is out there, which is basically tubing that is directly embedded in concrete. As far as energy sources are concerned, everybody's looking for a cheap energy source. An approved gas-fired or oil-fired water heater will make an excellent energy source. It's not going to have the longevity that a true boiler will. But if you decide that you want to do this, do not use the same contiguous water in the space heating system that you wash and bathe in unless you're really into getting Legionnaire's disease. And the solution to that is to essentially apply a flat plate heat exchanger between your radiant floor heating system and your gas-fired water heater as a heat source. Doing this, you won't have to worry about the bacteria growing in this heating system during the non-use summer months. And if you happen to be so unlucky as to be in a shower when this system pump turns on and you get showered with bacteria and you have a depressed immune system, you're pretty much guaranteed to contract bacterial pneumonia, which is commonly misdiagnosed as bacterial pneumonia, when in reality it is basically Legionnaire's disease. And as a survivor of Legionnaire's disease, I would not wish it on my worst enemy. I pity these people that have been through COVID, and I think I've been through pretty much the same thing. It felt like I was going to cough my lungs inside out. All right, let's move on to a radiant wall study. We had a job that we did for the Department of Energy, and it was basically a radiant wall installation on a Habitat for Humanity home. This is the actual radiant panel itself. Uponor supplied us with these aluminum heat transmission plates that we embedded into the face of the studs. And then we snapped our tubing into that. And then we added insulation behind it. And we used non-electric thermostatic radiator valves to be able to control the flow of hot water through this. So we have a modulating boiler, we have a modulating pump, and we have modulating heat controls. This is like the ultimate heating system. It only uses what it needs to be able to provide the comfort and maintain decent conditions within the space. Here's another radiant wall heating system. This is more of a European style of installation. Basically, they put the tubing in with some U-shaped channel track that holds the tubing in place and set it up so that it basically circulates again with non-electric TRVs, can be combined with radiant floors, can be combined with radiant ceilings. I have one room at my house up in the mountains that has radiant floors, radiant walls, radiant ceilings, and radiant windows. This is Robert Bain's basement. He did a retrofit panel into his system that essentially is a climate panel and works fantastic. He loves it. I love my radiant walls. You know, the ability to be able to absorb radiant energy is a function of, if you think about it in the form, radiant is a form of light wave. And if you have a flashlight and you flash that flashlight on your body from a ceiling or from a floor, the amount of shadow that you project basically dictates how much of that radiant energy you are actually absorbing through your body. So if you've got a body with a flashlight pointed at it at a right angle, the shadow that it's going to project on the wall behind it is significantly greater. So the radiant walls actually produce a higher degree of comfort from the standpoint of being able to absorb and feel that radiant energy than do radiant ceilings or radiant floors. Steel panel radiators. If you have not experienced these, this is a European standard. I have these in my house here in Denver. I love them. When I first installed them, the wife said, "Oh God, those are ugly." And I said, "Honey, nobody's even going to notice them. We have an annual party, our anniversary. We had 100 people in, and at the end of the night, you know, there's usually the dozen hanger-oners that are really good friends, and sitting in the living room. And I said, "So what do you guys think of my new heating system?" And they're like, "What? Where?" And they're all looking around. And I said, "That, the panel radiator." And they're like, "Wow, that's really cool." She never said another word about it. She loves them now. Very comfortable. This is the ceiling in my house up in the mountains. I put in 1/2-inch plywood across all of the rafters, and that gave me the surface that I was able to then mount this aluminum and foam heat transmission plate to the ceiling itself. In this particular application, I put on 2 layers of sheetrock because I've also got this tied to my solar thermal system. And basically, I wanted to be able to give myself the ability to be able to store some energy that I receive from the day to carry me longer through the night. So it works great. Here's some additional radiant ceiling applications. This is a microtube system showing before the bare side on the left-hand side, normal light. The right-hand side is the infrared light. There's an additional radiant ceiling application. Can lights. Can lights are really about the only thing that you have to take into consideration when you're laying these systems out. And it's relatively simple to work around. Every major manufacturer of tubing, by the way, Uponor, Watts, Viga, they all provide calculations for being able to do radiant ceilings now. And as a historic fact, radiant ceilings have been around longer than radiant floors have. A lot of people don't realize that. So here's an installation with the radiant ceiling heating system. This is a microtube system that comes out of Europe. They were in the process of trying to get this approved through IAPMO when I was working with IAPMO about 6 years ago. And hopefully they've gotten it approved by now. Here they are installing another method of radiant ceiling panel system itself. Here's a typical mechanical configuration showing a boiler. And you could have this radiant panel connected to whatever you want. It could be radiant floors, radiant walls, radiant ceilings. Supply water temperature is dictated by surface area and the load that you're actually trying to extract. And having a nice boiler also gives you the ability to be able to do domestic hot water. There's always a shortage of hot water in every house that has teenagers. If you haven't gotten involved with electric cable heat, I would recommend that you do. When we do a high-end house, a nice custom home, we will typically do both a hydronic radiant floor heating system in the bathroom as well as an electric radiant floor heating system. The primary reason being is that during the summer months, when you're not firing up a large physical plant, boiler, pumps, etc., you can still give the customer warm floors, and they like it even in the summer months. It's nothing greater stepping out of a shower onto a warm floor other than grabbing a hydronically heated towel. And towel warmers are something that I didn't really get into here a lot. It's kind of a vanity type of installation, but everybody that has a towel warmer that we have as customers love it. They rave about it. So there's the finished radiant floor electric tile system. There it is in a rough state. The disadvantage of these series cable systems is that if you do break the cable someplace, it's tough to find the actual break. It is feasible now. It didn't used to be at all. They've now got a system that they call the triad system, where they can actually come in with a sensor that will show you where the break in the electrical current is. And then you basically break up the floor and use Scotch locks to be able to do a good effective repair on it. Simple floor schematic showing that essentially you do want a temperature sensor on there so that you can limit it to 85 degrees Fahrenheit. This is the hot link. This is the cold link that goes actually to the actual thermostat, and they're basically breaking that 120 volts circuit with a line voltage thermostat. There's the contactor panel showing what would be necessary from the standpoint of distribution. There's a simple wiring schematic. Now I want to get into some sample hydronic radiant panels. This system that's up here on the top is the most popular and the least expensive. It's basically tubing that's on steel mesh that's poured into concrete. And notice this insulation. This is a requirement. It's not an option. Used to be an option. It is currently a code requirement. You've got to have insulation on the bottom as well as on the edges to be able to avoid the side loss of that slab. So then we have a thin slab system, which is basically what we call staple down. You staple tubing to the top of the plywood subfloor and then cover that with either 1.5 inches of gypcrete or in some cases 2 inches of lightweight cement. And we have the plate system above the floor. And the key advantage of all of these systems is high conductivity on the side that you're actually trying to heat. So this requires a lower operating temperature than will this system down here on the bottom. The system on the bottom is staple up, which we do not do within this organization. I work for a company called Advanced Hydronics in Denver, and we refuse to do this. It's too noisy, requires too high of a temperature of operation, too many problems in general with that system. We convert a lot of these to this heat transmission plate type of system, but we refuse to do this. And you will notice that basically if this is a 16-inch joist, you basically have tubing at 4 inches on center. That's pretty labor intensive. Some people don't value their labor. We do. We want to make sure that everything that we do is done as properly as we possibly can. But in retrofit applications, we will come in from below the floor. We'll install an extruded aluminum heat transmission plate and then put our insulation beneath that and end up with an excellent radiant floor heating system. This requires water temperatures of around 140 degrees. This is going to be around 105 to 110. This system down here on the bottom can be as high as 180 degrees Fahrenheit requirements. Waste of energy. All right, so from the standpoint of wall and ceiling panels, it's essentially the same thing that we looked at before, except in different positions. So this is a heat transmission plate that's basically being applied to a system Again, insulation, you're going to have insulation in the backside of this attic anyway, but Siegenthaler and a lot of other people's recommendations is to double that R value. Whatever your minimum is, double it just to minimize the back loss from that panel. Tubing embedded in the actual cement itself, lath and plaster. Wall plate systems, embedded tubing, steel panel radiator, either vertical, horizontal. And we've also mounted these on ceilings in certain situations where we were short on space. And then radiant baseboard. Radiant baseboard, I think there's maybe one manufacturer still around. The majority of the output of this device is basically going to be in the form of convective energy. And obviously the surface area is limited, so it requires a pretty high approach water temperature to make it work. But again, it is an option, something to consider, something to look into. So slab on grade systems, this is a good breakdown. This is that insulation detail about the edge that I was talking about. Pardon me. You're right, Tom, I lost my voice. I've been talking all day.
You want to
No, I'm
take a
fine.
break, Mark?
I'm fine. I got some tea here. So nobody wants to see a big strip of blue insulation running around the edge of their slab. I don't blame them. I wouldn't want to see that either. So the key is to take some 4-inch pieces of insulation, 4 inches in thickness or in width, and essentially cut a 45-degree chamfer onto that insulation. And basically you end up with a concrete finish that goes all the way to the edge of the wall. You see no blue at all, but you end up with this thermal break on the edge, which stops you from sending heat out the wall and causing Johnny jump ups to grow in the middle of January. Enough on that. So thin slab, this is also a very popular method. Essentially, what you do is you will staple down tubing to the actual top of the subfloor itself. In the case of gypcrete, they put an adhesive down to allow that gypsum to actually bond to the plywood subfloor itself. If it is a lightweight concrete, you want a bond breaker. It's actually a sheet of plastic that you put down onto the floor because the concrete has a higher coefficient of expansion. The gypcrete always remains somewhat liquidous because of the amount of sand that's in there. Whereas the lightweight concrete is going to get hard. It has a high coefficient of expansion, and if it bonds to the actual plywood subfloor itself, it will turn itself into a jigsaw puzzle. You will have cracks everywhere, and you don't want that. So they require that in the case of a lightweight concrete that you put down a bond breaker, but in the case of gypcrete, you actually put a spray adhesive applied to it so that it will actually bond to the actual plywood subfloor. And again, insulation is not an option. It's a requirement. There are some insulations that are out there, foil insulations. Quite honestly, I think it's junk science. I've tested it under slabs. It gets compressed. It has essentially the same R value as a 1/2-inch piece of wet sheetrock. Not very high at all. How are we doing for time, Tom?
Good to go, Mark.
Good. All right, so here's the thin slab concrete application. And note that you have a polyethylene bond breaker that has to be applied to the top of the subfloor before the tubing is stapled down and before the concrete is actually poured. And it's also recommended that if you're going to have any tile, that you put an anti-fracture membrane over the top of that concrete so that when you do bond tile to it, that you won't get any echoing cracks to that actual subfloor itself. Here's an above floor plate system. And again, the advantage of this is that your heat source is actually on the top of the plywood subfloor. The subfloor, if you're coming in with heat transmission plates from below, represents a resistance value that you have to overcome in order to get heat to this final surface where it's emitted into the space. In the case of radiant floors, you can have these plates laid out. You can have sleepers if you're going to put hardwood over the top of it. Very compatible with pretty much any finished floor. It's always a wise idea to have this conversation with the consumer early on about what their expectations are as it pertains to floors. It's okay to put throw rugs down to kill the bounce effect of echoing within a building itself. But if they cover your floor with carpet, number one, we're putting heat into your floor. The reason for putting down carpet is because you don't like cold floors. We're not going to have cold floors. We're going to have warm floors. So please don't put a blanket on my radiator. But if you absolutely have to have pad and carpet, as thin and as dense a pad as possible, and as thin and as dense a carpet as possible. And there are actually radiant rated pads and radiant rated rugs that are available to accomplish and achieve that goal. So, it's tough to tell them what they can and can't do in their own home. But if they say, no, I'm going to cover the floor with carpet, then say, okay, I need your signature here in this contract acknowledging that I told you not to do this, so that when it's 10 below outside and your house won't go above 50, that we don't have to remember this conversation. All right, so here's the retrofit application where you're putting the heat transmission plates in below the floor. It has to overcome the resistance value of the plywood subfloor itself, plus whatever the finished material is. So it is inherently going to require a higher approach water temperature from your heat source. All right, if you're going with ground source heat pump, can you hit 140 degrees? No, you can't. Typically 115 degrees, 115, is going to be the maximum temperature that you'd be able to get out of it. Now, we have a lot of hybrid systems. The problem with having a ground source heat pump system is that if you're doing domestic hot water preheat, 115 is not hot enough for end use. So we need something to raise it the rest of the way. If they don't want to use electricity, then the alternative is to set a boiler and a reverse indirect for domestic hot water, which then gives you the ability to be also pick up where the ground source heat pump off. So if you decided that you needed 140 degree Fahrenheit water based on this application, then basically the ground source heat pump is good up to 115. And then from 115 up to 140, the ground source drops out and the boiler turns on and picks up and takes over for it. So it also provides you with copious amounts of domestic hot water for those teens that feel there is no end to hot water. And it also provides you with the temperature that you need to be able to achieve this. If you're designing a system around a ground source heat pump and you don't want any augmented heat from boilers, then you've got to make sure that the house has got high R values and that your floors or walls or ceilings or whatever you've got have got enough tube density and heat transfer that it will work well with that low water temperature of 115 degrees. All right, this is an engineered subfloor system. This system is actually manufactured by a company called Warm Board. It is a combination structural panel as well as a radiant panel heating system. If we are dealing with somebody that wants strictly ground source heat pump, this is our minimum standard for the upper frame floors. The basement floor, concrete, no problem, high conductivity factors. On the upper floors, if they want to go with ground source heat pump, this is our minimum standard. The company will do the CAD layout for you. You give them the floor plan. They will show you where the panels go. The panels are actually installed by a carpenter, which is a less expensive labor factor than a hydronic heating contractor or a mechanical contractor. So that helps hold the cost down. But I will caution you, this is one of the most expensive floor heating systems in the world, but it's also the most efficient. It's been tested, it's been proven. It is worth the money. I've never had anybody argue with me after the fact. They all go, "Ooh, that's expensive. What's the alternative? I haven't heard about gypcrete." Well, yeah. Well, what they don't tell you about gypcrete is that you need 2 sole plates. You're going to have 15 pounds per square foot additional dead load that you have to handle, which means a deeper floor joist. It also means a lesser span between the support structures itself. So there's a lot of things that go into using gypcrete that don't just hit you in the face as being an additional cost. So when you take that into consideration, the gypcrete's really not all that much cheaper than the engineered flooring systems, and the engineered flooring systems work significantly better with lower water temperature of approach.
Yeah.
So let's talk about some radiant ceilings. They can operate at a higher temperature than floors, primarily because you are not in contact with them. The radiant floors are limited to 85 degrees Fahrenheit by code, and that's not a physical limitation. I've seen radiant floor heating systems as hot as 120 degrees. Couldn't walk on it, but hey, it was hot. It's a human physiology limitation. Your skin surface temperature is 85 degrees Fahrenheit. If your skin is in contact with the surface greater than 85 degrees Fahrenheit, you have a gland about the size of a walnut at the base of your skull that thinks that your body's going to overheat, and it immediately sends your body into cooling mode, which when my wife does it, she calls it glistening. If I do it, it's called sweating. I've never understood that, but in any case, I don't argue with her, and you don't want her glistening. So keep your floor surface temperatures below 85 degrees Fahrenheit with the exception of rooms where people are typically less clothed and possibly wet, which would be a bathroom. And in a bathroom or a pool, you're allowed to go as high as 90 degrees Fahrenheit for a maximum floor surface temperature. Radiant ceilings are not affected by floor coverings. If they want to put bare rugs on the floor, go for it. Responds faster than floors. Absolutely. When it's set up right, the acceleration time is significantly less for a ceiling than it is a floor because of the connected mass. It starts putting heat out almost immediately. And here's the interesting thing is it will warm the floor as well as the objects in the room below. A lot of people go, well, I like radiant floors. They're nice and comfortable. Well, guess what? In my house that I've got radiant ceilings in, my floors are never cold. They're neutral. I can walk around on my bare feet and they do not feel cold. They feel neutral. And it's real cold outside and the panels are really working hard. The floors actually do feel warm. Take up less vertical space. This is an issue as it pertains to high-rise buildings. Every inch of space in that vertical profile is money. And so if you've got a 100-story building, then you just saved 100 inches. Guess what? You just added an additional floor to that retail space. So much better. Adds very little weight. Basically, the weight of the tubing and the fluid that's on the inside of the panel itself, the radiant panel itself is nil. It's very little weight at all. Induces very little air circulation. As I mentioned to Tom, I've got a system up in my house up in the mountains with the radiant ceilings that I have ceiling fans. And the ceiling fans are tied into my energy management system. So when I am in acceleration mode, the ceiling fans are on. Normally you get zero contribution as it pertains to the convective cycle from a radiant ceiling because hot air doesn't want to fall. It wants to rise. It wants to stay at the top. If I turn the fan on and start moving that air around, boom, I double the output of the panel. So look at some radiant ceiling panels themselves. It's basically the same thing as a surface mounted radiant floor, except it's turned upside down. There are some systems that use a T-bar system that basically have a heat exchanger that's built into the actual drop-in panels that would normally go into a ceiling that basically provide you with excellent perimeter radiant heating system. This is very common in a lot of large commercial buildings. They essentially use this to counter the effects of the cold glass, which is right here, which everybody goes, well, why do they always put base boiler underneath the window? Because they're trying to counter the cold sucking effect of that glass with a curtain of warm air between you and that cold window. And essentially you can do the same thing with the radiant ceiling panel by putting this radiant ceiling near the exterior. It basically counters the negative effect of the cold windows that are trying to pull heat off of your body. Here's a radiant wall plate system that's, again, essentially the same thing as doing a surface mount radiant floor, except it's turned vertically. And you've got nice, good tiles that you can put on here. My house in the mountains, I actually have tongue and groove wood. The whole interior, it's a cabin. So I tried to make it look as antique as I could. And it worked fantastic. I love my radiant ceilings. I love my radiant walls. I love my radiant floors. I love my radiant windows. I love my panel radiators. I love my cast iron radiators. I love
You
radiators.
have any bumper stickers on your car?
I do, as a matter of fact. On my car, it says, "Have you hugged your boiler today?" Unique. I have another bumper sticker that says, "Friends, don't let friends pour concrete without having plastic tubing in it." Yeah. I'm into radiant. All right, so let's talk heat sources. We've got gas and oil fired boilers in both condensing and non-condensing mode. I don't know, I have 3 oil fired boilers here in Colorado. I know you guys have got a lot more back there in Ohio. Have they ever advanced any condensing oil boilers that did it turn out to be a nightmare?
Not that we've seen.
Okay, I know Baderis is, or not Baderis, the other one starts with a B. Burnham. Burnham had something that they were working on there for a while. All right, so hydronic heat pumps, either air or a ground source heat pump, are perfectly compatible with hydronic radiant heating. Approved water heaters. You can't just grab a water heater from Home Depot and slap that puppy in if you're going to get a permit on it. It has to be certified for application as a space heating appliance. Combination water heaters that do both space heat and domestic hot water are perfectly compatible. And other sources, which include solar, solar thermal, solid fuel, wood gasification, thermal storage, that battery storage, that ice battery storage system that I showed you, they're all compatible. So you've got gas-fired boilers, you've got water heaters, you've got pretty much anything that you want available on the market today can be applied to these systems. What you have to be cautious of is if it's a condensing appliance, you'd like to keep it in the operating mode of 140 degrees or less. You can spend a little time outside of that range, no big consequence. But if it is not a condensing appliance, you've got to make sure that it doesn't condense or you will have a short life expectancy for that appliance. And that's an area that is so overlooked by so many contractors. They go, this will work. They'll hook it up straight, primary, no primary, secondary, no variable speed injection, nothing. And then we get the call, this boiler is rolling out really bad. And we get in and find the heat exchanger is condensed, it's corroded, and it's basically dead at that point. So we have water to water heat pumps. We also have air to water heat pumps. Basically in the current realm of heat pumps, and I've been talking to the water source heat pump manufacturers for probably 40 of my 45 years of being in business. And I keep asking them, when are you guys going to come out with a variable speed compressor? It's not a new technology. You just need to apply it. One of them finally did. I believe Water Furnaces finally brought out a variable speed compressor. But when you don't have a variable speed compressor, you've got to have a buffer tank. The reason for this buffer tank is the hardest thing that you can do to this compressor is to start it. And when you start it, you want it to run for a long time. And when you're done with it, you want it to be off for a long time. And the only way to achieve that is to have basically a large storage tank that when it turns on, it runs for a long time. When it turns off, it stays off for a long time. Well, with variable speed, this goes away. The buffer tank is no longer necessary. The compressor is basically going to vary its speed based on matching demand to the load. So hopefully those folks have gotten it together and we'll be out with something real soon. Again, combination systems with a heat exchanger. My personal preference is to set a wall hung boiler with a reverse indirect water heater. Everybody in this room, I'm sure, is familiar with an indirect water heater, which is basically a large storage tank with a small coil on the bottom of it. You circulate 180 degree Fahrenheit water through that coil, transfers heat to the potable water on the inside of it. A reverse indirect, as the name implies, is a large storage tank that has a large copper heat exchanger on the inside of it. You run boiler water through the tank. You run potable water through the coil. It is essentially 99% efficient. So if you've got a 300,000 BTU an hour boiler, it's basically going to take 99% of that 300,000 BTUs and turn it into domestic hot water. The neat thing about that particular application is that it requires an approach water temperature that's essentially only 10 degrees hotter than your desired target water temperature. So if you want 130 degree Fahrenheit domestic hot water temperatures, which I feel is very reasonable, you only have to heat that storage tank with 140 degree Fahrenheit water in order to be able to get that good hot water temperature out, which means that your modulating condensing boiler is going to be in the condensing mode even when it's doing domestic hot water production. Whereas with an indirect, with a small coil, you're going to have to go to 180 degrees to be able to kick the BTUs into that storage tank, which takes that appliance out of condensing mode. All right, let's talk about ventilation and cooling options. Exhaust fans. We've got heat recovery ventilators. We've got energy recovery ventilators and DOAS units. And for those that don't know, DOAS stands for do as I say, not as I do. No, it doesn't. It stands for dedicated outdoor air systems. I slap myself sometimes. I tell you, I lose control, especially this late at night. Here in Colorado, we use a lot of evaporative coolers, primarily because we have no humidity in our air anyway, and it feels great and it works well from the standpoint of being able to provide cooling. You get back east where you've got high humidity, it will not work. There are some systems that will work. There's a system on the market called Coolerado, Coolardo, just like Colorado, except Coolerado. That is actually it's an indirect evaporative cooling system. It has a small membrane between the evaporative side and the room side so that it does not increase the humidity within the space. It just basically depends on the evaporative capacity of that unit to transfer heat. High velocity cooling and heating systems are an option, and conventional air conditioning. Now, these are basically, we're talking about people that are doing hydronic radiant steel panel radiators, hot water baseboard, whatever, this gives them the option of being able to add cooling to their capacity. And then we have radiant cooling. Radiant cooling, first thing I heard it clear here in Colorado, the very first thing that I heard that popped into your mind was, what about the condensation? It's the first thing that popped in my mind too. We'll talk about it. Hybrid solutions, combinations of both hydronic and gas forced air, and then basically some small variable speed fans to control the infiltration within the house itself. Tom and I grew up at a place called The Wall. That's where we first met, Dan Holohan's place. You guys have probably been there. And way back when, it was hydronic versus forced air, and forced air was the enemy. And Dan still, to this day, believes that forced air is our enemy. And from the standpoint of being a good comfort contractor, we have to provide ventilation. If we don't, we're not doing our job. And the only way that you can provide ventilation is to move air. So it is a necessary evil. It doesn't have to be 100% carrier of the comfort within the house, but it is something that should be taken into consideration, either a heat or an energy recovery ventilator. In Canada, they have a process that they call build it tight and ventilate it right. And it works very well. You have a control over the amount of exfiltration. They build these things so tight that when you close the door, the windows go boo, and then they ventilate it so that they make sure that you've got a good, adequate supply of fresh air coming into the system itself. High velocity cooling systems, if you have never seen one before, they are interesting. Basically, you end up with a large trunk line that runs through the attic or the basement with branches that take off and terminate basically at the ceilings. First time I saw these, I thought, man, that's going to be noisy. And I'm thinking about sitting on a jet and looking up at that jet that's pouring air on me going, I couldn't live with that. I don't know how they do it. They've got a noise attenuation device that they put on the end before it goes to the actual termination itself that makes these things almost virtually silent. You have to be careful about where you put your vent terminations. If there's going to be a chair there, you don't want to be dumping cold air on people, but it is an option. We've done quite a few of these systems here. It has to be done right. If the manufacturer says you need 13 vent terminations on this thing and an return air vent of this, you'd better do that, because if you don't, it's not going to perform the way that they said that it would. So I want to talk about managing the consumer's expectations. We spoke about it earlier. The biggest key selling factor of radiant floors over the years has been warm floors. In fact, Uponor had an image of a foot, and that foot was warm and happy. And I hold Richard Trethewey personally responsible for the radiant floor revolution. He showed up on this old house with a 1,000-foot coil of PEX on his shoulder and said, we're going to do radiant floor heating today. And that was the beginning of the radiant floor revolution. And every woman in America was watching that show, I swear to God. And they grabbed their husband and said, we need radiant floors. And it was great. I mean, that's basically what caused radiant floor heating to take off. And it's great, except when you start getting into situations where you've got high efficiency homes that have loads of between 2 and 5 BTUs per square foot per hour, the floor will never be warm. And you have to explain that to the consumer when they go, yeah, I want radiant floors. Then you explain to them, well, you know, we can do that, but it's expensive. And you probably will never even realize that the floors are warm. Will you be comfortable? Absolutely. You will never be more comfortable, but I have to control your expectations. The floors will actually never be warm. So I always go in to talk to people about warm floor concept versus radiant comfort. We affect the mean radiant temperature with our radiant panels, regardless of whether it's a floor, a wall, a ceiling, a panel radiator, cast iron radiator, whatever it happens to be. Basically, we're trying to control radiant comfort within that space. And by doing that and explaining that to the consumer, then you avoid that issue of them calling you up when it's a little cold outside going, you know what, my floors have never really been warm. What did I pay all this money for? I thought I was getting warm floors. Well, I hate to tell you this, if your floors were warm, you'd be opening windows. You'd find out what the mean of mean radiant temperature really means. So yeah, here you go. People have spent millions and millions and millions of dollars as manufacturers convincing everybody that every house should have warm floors and that every foot in that house should be warm. And that's great. In a house that's got a load of 30 BTUs per square foot per hour, absolutely. You can expect floor surface temperatures of 85 degrees Fahrenheit when it is 0 outside. Should change if you've got a good outdoor reset controller on it. It will change the temperature of the water based on the temperature outside. But when it gets to design condition, which we just came through for the last 5 days, we're actually below design condition. You can expect the floors to be warm unless it's a super insulated house, in which case it's probably not going to be perceptibly warm at all. So be aware of high efficiency homes and floor surface temperatures. Basically, it calculates out to, if you've got a 5-degree load, it's 2.5 degrees Fahrenheit surface temperature above the ambient. Right. So if they're maintaining 70 degrees within the space, they can expect the floors to be 72.5 degrees Fahrenheit. Their scan is 85 degrees Fahrenheit. Heat flows from hot to cold, so it's not going to feel warm. Just a matter of controlling the consumer's expectations. They actually appreciate it when you talk to them about it. They go, oh, nobody else has explained that to me. I'm glad you did before I spent all that money and realized that my floors were never really going to be warm. But there is a need for warm floors. Where are best utilized? In the bathroom, where you usually are wet and naked. Makes all the sense in the world. Keep that floor at 90 degrees Fahrenheit. That's Robert Bean's girlfriend, I'm pretty sure. Right, so floor, ceiling, or wall. What are the advantages? What are the disadvantages? Contact with people? No. No contact with people on the ceiling unless you've got grandkids like mine, in which case you got to peel them off the ceiling. Floors, yes. Walls, possibly, yes. Response in less than 30 minutes. Is a floor or is the ceiling going to heat up quicker? Absolutely. Floor, no. Walls, yes. These two yeses basically allow you to use a programmable setback thermostat. Programmable setback thermostats are not compatible with radiant floors. If they've got radiant floors, we tell them to set it and forget it. If you'd like a cooler sleeping environment, turn it down to 65. Your other spaces, keep them set for around 68 to 72, depending on how much glass you've got within that space. Response within 3-hour period, I give floors a yes, but we've had a lot of houses here in Colorado that are up in our ski areas that the consumer paid to put radiant floors in. They show up Friday, 5 o'clock, the house is at 50 degrees, they turn the thermostat up to 70 degrees. About the time they're ready to leave at 3 o'clock in the afternoon on Sunday, it just starts getting comfortable. So a lot of those people have ripped the boilers out of their houses and have put gas forced air systems in because their response is immediate. Well, really, it's not. You're still feeling the cool effects of the mean radiant temperature, but they feel the benefit of the warm air coming in. So their brain says, hey, you're happy, you're comfortable, you're getting heat. But our recommendation is, hey, put a thermostat in there that is internet active, that you can turn this house up 2 days before you're going to be there. And when you show up, it will be perfectly comfortable. And you won't waste any energy to speak of. It's going to take whatever it needs to be able to get it to the condition that it needs. So absolutely, if they want radiant floors, talk them into an internet active thermostat that they can turn up 2 days before they're going to get there. And all the complaints about the radiant floor heating system doesn't react quick enough are going to go away. So from the standpoint of heating, absolutely, ceilings are great. Floors are excellent. I'm not going to argue with you guys. I love my radiant floors. But from the standpoint of installed cost, it's expensive. I have to put a minimum of 1 foot of pipe per square foot of floor space because I sold the consumer on warm floors. And if I leave any tubing out of that floor, as soon as their foot hits that cold spot, they're going to be on the phone going, what did I pay you $30,000 for? I found a cold spot in my floor. What's wrong? Nothing. You know, it just wasn't necessary to put it in the middle of the house like that because there is no heat loss there, but you know, that's just the way it works out. So with a ceiling, we don't worry about it. We put in what's necessary to counter the load. They're not going to be walking on the ceiling, unless they're my grandkids. And basically you can put an install cost. Typically it's about a 4-foot perimeter around the exterior of the building for a high temp radiant ceiling panel system. If they want to go with alternative energies, then you may have to cover every square foot of that ceiling. But if they want to put bare rugs on the floor, they can and not affect the performance of that panel. How about radiant cooling? Is the ceiling
Mark?
excellent?
Mark,
Yes.
How are you
Yes.
loading the ceiling?
How do you what?
How do you calculate your load on the ceiling?
As far as the output of the panel is concerned,
Yes.
it would depend on the radiant tubing manufacturer to provide you with that information. And it's based on the amount of sheetrock that you put over it, which is basically resistance value. And it works out to, I've got the numbers someplace bouncing around in my head. You lose the convective capacity of a ceiling. You've got 100% radiant, but with a radiant floor, you have convective and conductive and radiant. And when you're dealing with a ceiling, you're dealing primarily with just radiant, period. There is no conduction and there is no convective at all. So you have to calculate it based on water temperature, tube density, resistance values of the sheetrock that are being applied. But basically what I have found is in a building that has a load of around 30 BTUs per square foot per hour, if you hit that with 140°F water, you can do a 4-foot band perimeter around that ceiling, and it will keep the core as a general in a very comfortable condition.
Thanks.
But I always recommend that you depend on the manufacturers. Don't guess at this stuff yourself. You'll get into trouble. They have programs. They'll be glad to do it for you. They're going to sell you tubing. They want to make sure it's done right too, because they don't want to end up being party to a lawsuit. So cooling, back to cooling. Yes, absolutely. A ceiling is an excellent application because where does hot air go? Hot air does rise in that case, and it will affect the radiant temperature within that space. You can feel the heat that's stacking up at the ceiling. Well, there's a cold source there. It absorbs that heat. Basically, all you have to worry about at that point is being able to handle the latent energy, which you can do with dehumidification or a cold coil, some means of being able to control the humidity within that space and keep it away from the dew point. All of these manufacturers that put these controls out are basically watching the dew point, and they can do one of two things. They can either manipulate the dew point by reducing the humidity or manipulating the temperature of the surface itself. Ideally, if you control the humidity, you'll never find your panel anywhere near the point of condensation. We're getting close. We're 92 of 123 slides. So what about the production of condensation? If you have to wear a face mask and glasses, you may be entitled to condensation. Condensation is definitely a concern. We've got some mechanical rooms. The insulation that you put on these pipes has got to be vapor sealed. The problem with vapor sealing is maintaining 100% vapor seal for the full length of that insulation. And if you get one void, basically condensation, humidity, temperature, pressure, everything basically flows from regimes of high concentration to regimes of low concentration. And in the situation where you've got a cold pipe, it's going to suck moisture into that pipe through any lap seal that was voided by, expansion and contraction or some other tradesman that cut the insulation, whatever, and you are going to get the production of condensation. So as I mentioned, what they typically try to do is to control either the surface temperature or the humidity within that space and avoid the possible generation of condensation. I've seen a lot of buildings that have radiant floor cooling systems in them. Was in one in Calgary, Canada. It's an airport up there. And I could actually see where the tubing was. And when I asked Robert Mean about it, he said, yeah, he said, I'm familiar with that. He said, they let their humidity get out of control once. And he said, that's basically what happened is the marble tile basically absorbed the moisture at that point. And you can see the tube traces, but it was no big deal. They corrected it pretty quickly. So what about fresh air ventilation? You have to control fresh air ventilation if you're going to do radiant cooling. If you don't, you're going to get situations where if somebody leaves a window open, they like to sleep with their window open, then basically you're going to have a lot of humidity that's going to come in and raise the relative humidity within that space. That's uncontrolled infiltration. And in a lot of situations, we recommend that they put a proximity switch on the window. If that proximity switch is open and indicating that the window is open, you get no cooling. All the windows have to be closed, and they have to be closed as tight as possible. Okay, maybe not that tight, but you have to have control over the windows, absolutely. If you don't, you're going to get into trouble. Speaking of windows, any way that we can possibly reduce our gains through fenestration, internal gains from lighting, equipment, etc., is going to reduce the load, which will increase the percentage of the load that can be carried by the radiant panel. Our building here is radiantly cooled. We've got radiant floors. We've also got radiant ceilings. This building is one of the most comfortable buildings I've ever been in at 78°F. It feels like 72°F when the room temperature is 78°F because we're controlling the mean radiant temperature, and we're also controlling the relative humidity within this space. These windows that are up here in the upper right They're actually an electrochemical type of window that can be programmed for a degree of darkness. So if you want them 100% dark with zero fenestration at all, you can program them and there will be no solar gain coming in, which you have to worry about. That is one of the key advantages of a radiant floor cooling system. Is if you've got fenestration, it's occurring on a surface that's already cold, so it's absorbing most of that solar fenestration that's coming through the window. The other thing that has been done with windows, I mentioned it earlier, and I'm sure it piqued a few people's ears and interest, is radiant windows. My house up in the mountains, I have radiant windows up there. Essentially what they did is they took the low E coating that's on the glass that's supposed to reduce the long wave transmission of energy through that window, and figured out a way of being able to make an electrical connection to that glass. The glass has a resistance value that is in squares, and it's basically 15 ohms per square. People per square foot, per square yard, per square wet, per square. If it's 1 square mile of glass, it's got 15 ohms of resistance from one side to the other. If it is 3 foot wide and 4 foot tall and the bus bars are on the long side, 3 divided by 4 is 0.75. So it would be 15 ohms times 0.75. So roughly 10 ohms for that shape of glass with the bus bars on the long runs. I'll tell you, in all the years that I've been doing this, this product has to be one of the most fantastic products in the world. I spent 10 years trying to develop to convince an investor that this is worthwhile to do it. The Europeans understand it. There's numerous radiant glass manufacturers over on the European market. One of them is here in the United States. The problem with glass is it's very heavy, it's very expensive, and it breaks real easy. So when you ship it in a container from Germany or from Russia or wherever it's coming from, over here to the United States, you may open up a container full of broken glass, which is going to be tough because then you will have to end up putting plywood on the windows of this brand new house, waiting for a new shipment of windows to come in so that you can finish the job. So windows are definitely interesting. They're cool. I've applied them not only in my house, but a couple of different projects. They work fantastic.
I'm confused. Radiant floor cooling, how could that be comfortable? Wouldn't the floor be cold all the time?
The floor isn't usually taken to less than 70 degrees Fahrenheit. Thank you for bringing that point up. You could actually take the radiant floor cooler than 70 degrees Fahrenheit, but then it creates what we call the morgue effect. That floor is so cold that it's sucking so much heat off of your body that you feel like you're on a cold slab in the morgue. So there's a limitation, and that is one of the limitations is you can only take that floor to 70 degrees Fahrenheit before it comes uncomfortably cold. Therefore, you'll never be able to carry 100% of the load with the radiant floor. You need some other means of augmentation cooling, and that's typically done with a fan coil or a chilled beam. There's a whole lot of different options that you can use to pick up the balance, but you absolutely cannot do anything with a latent. You need either a dehumidification system or a cold coil that you can extract the moisture out of the air and control that relative humidity within that space. But good question, valid point, thank you. So is radiant cooling a proven technology? How long do you think radiant cooling's been around?
I don't know. Never heard of it. Long thing.
Forever.
This is the Bangkok Airport, Suvarnabhumi International Airport in Bangkok, Thailand, has been radiantly cooled since 1970. And talk about nasty loads. This ambient temperature is around 100 degrees Fahrenheit. Relative humidity is at 95% relative humidity. And you've got a moving load that goes through this airport of like 250,000 people per day. Every one of them is breathing, producing additional humidity, etc. This building has been radiantly cooled since 1970. So it's not a new technology. It is properly applied, and when properly done, can be extremely comfortable and also extremely energy efficient. So nothing new on that particular realm. In the case of doing radiant slabs, you absolutely have to have the insulation below the slab itself. The other thing, if you're going to do radiant cooling, is you have to be able to dictate what this final finished surface is going to be. Our office here is basically polished concrete floors. Our preference in a residential application would be a hard stone or a hard tile surface. What you cannot use is hardwood floors. If you try to put a hardwood floor over this, hardwood floors are hydroscopic. They will absorb and release moisture at will. And unfortunately, it also changes the dimensional stability of the actual material itself. So if the customer says, yeah, I'm interested in radiant floor cooling, then you actually have to have control over what they put. You cannot put pad and carpet down. It will trap the moisture. You'll end up with a black mold issue occurring beneath that actual surface itself. So you have to be able to control it. If they want to retrofit that radiant panel onto the top of an existing concrete floor, they make these channel tracks that you can either shoot or glue down to the floor, snap your tubing into it, and then pour an additional coating of concrete over the top of that again. Again, insulation on the bottom side of this slab is critical. It's tough to do if it's a slab on grade application. There's no way that you can actually put insulation underneath there. But if there's any opportunity of being able to put insulation on the bottom side of that, you have to do that to control the directional flow of energy. Otherwise, you'll get downward or back loss that'll cause a crawl space or a basement to overheat, and it will cause the space that you're trying to condition to underheat. And the typical response is, well, let's turn it up. So they turn the operating temperature up. It makes a little bit of a difference on the top, but it also compounds the back losses into the space below and makes it even warmer yet. That's where we see the Honeywell round thermostat that's been ripped off the wall and the bimetal spring has been completely stretched out. Hey, thought they'd get that puppy to quit heating. Thin slabs, floor applications, again, you can do this. You can do this as a radiant cooling panel, but again, you've got to control what the finished floor material is. Do not allow pads and carpets. Small throw rug here and there is okay, but tell them you can expect to see a little bit of moisture on the bottom side of that thing if it gets real humid in here and you're not able to control the relative humidity. These floor plate systems don't work as well because you're dealing with the resistance value of the subfloor plus the finished floor between the heat transfer plate itself and the actual material that you're trying to cool or heat. Now these work much better because you've got the heat source on the top of the structure and less resistance value between the tubing that's carrying the heating or the cooling medium and the actual final surface that's going to be emitting that temperature. Radiant wall panels can be done vertically, they can be done horizontally. This is actually Bob Rohr. Some of you may have heard of him. He works for Caleffi, and Bob came up with this idea. The key to doing this, and I hear this again, I'm kind of like that guy on, used to be on TV where he could read people's minds. What about hanging pictures? Good point. I don't want people finding any tubes in the wall. So my recommendation, if they go with this method, is to buy one of those inexpensive thermometers that you stick in your kid's ear and you press the trigger. That's essentially a non-surface contact infrared thermometer. So if you point that at the wall and you scan back and forth, you can see where the hot spots are. And that's where you don't want to put the nail to hang that picture. Personally, I prefer to do wainscot height because the only people that are going to be hanging pictures below 4 foot are kids, and they're not going to be using any kind of a fastener. They're going to be using tape. So it's very rarely an issue as it pertains to doing radiant walls if you've gone to a wainscot height of 4 foot. And then anything else above that, there is no tubing. They can use railroad spikes if they want to hang their pictures. You guys are awfully quiet. Radiant ceiling panel systems, again, typically they are installed at parallel to the floor joists themselves. In my case, I had a ceiling that I had to put in 1/2 inch of plywood to give me a surface that it could actually mount my radiant panel to itself. But there's a lot of different types and ways of configuration. Warm board, as a matter of fact, makes 2 different panels. They make one panel that's called an S panel that's a subfloor that's structural. They also make what they call an R panel. The R panel comes in 2x4 sheets. The S panel comes in 4x8 sheets. It's 1 1/8 inch thick. If you wanted to put that panel onto the ceiling, you could. It's kind of heavy, but you could put it onto the ceiling. Just make sure that your rafters are rated for that additional load that's being attached to them, and essentially set yourself up where you've got a good radiant ceiling heating system. But the R board is 3/4 of an inch thick, so it's not as heavy, has the same highly conductive aluminum sheet on it, but you can essentially set up whatever you need in the way of a radiant ceiling heating or cooling system. There are also some commercial radiant heating systems that are available that are made to drop into a ceiling to basically displace the ceiling panels themselves. You can see that you've got copper tubing with an aluminum heat transmission plate. So the final heat emitting surface on the room side is highly conductive, requires a relatively low water temperature. But if you hit it with a high temperature, it will put out a whole lot of BTUs. Then our European style panel radiators. Some people look at these things and they go, nah, I don't really like it. You go over to Europe, this is a standard. You get into Germany, this is the norm everywhere. And they are very comfortable and virtually silent. Electric embedded cables, they've got them set up in a pre-weaved system. Let's see, it's Watts Radiant that produces that particular product. There are also films, TFE films that basically change your resistance with temperature. So if you've got a situation where you've got a significant amount of south-facing glass and you've got sunshine coming through that's hitting that floor, that TFE panel can sense that, changes its resistance so that it puts out very little heat. Whereas on that same circuit in parallel, over on the other side of the room where there is no sunshine on the north side, it's cold and that panel resistance is different and it actually is putting out more heat. So I would strongly recommend that you look into those. Favorite company that I have for that is a company called Warmly Yours. They're out of Chicago and they carry everything. They also have design engineers on hand to help you with your design, load calculations, etc. All right, let's talk about a little bit of non-radiant convective hydronic systems. The non-radiant basically is a fan coil unit. So you've got either a hot water coil or a cold water coil, a filter to pre-filter so that you're not plugging the coil with lint, dog hair, etc. And the fan that's your prime mover to move it out. There are also some units that they put the coils on the outlet side of the blower. It's not really a requirement from either side. It really all depends on the application. And then we've got this particular system is called a valence sealing system. And it can provide you with either heating or cooling. This is what it looks like. It's basically a large baseboard convector that instead of being mounted down on the floor, it's mounted up here at the ceiling. And essentially you get the opportunity to be able to produce heat. It doesn't heat as well, but it really provides some good cooling because essentially the hot air comes in, goes through the fins, the cold air drops down the wall, but it has a condensate tray that runs the full length because you are going to condense the moisture out of the atmosphere itself. Edwards Engineering is a company that still makes that product. Then we have non-radiant convective systems with a coil that's essentially mounted at the ceiling, and they can be in either active or a passive application. In the case of an active, they actually have a blower that's circulating room air through that whole unit. So you get substantially more BTUs of cooling out of a forced system than you would through a natural convective system. And then we have some additional ceiling bling. This is a single blower that basically has directional vanes that you can direct the air kind of out 360 degrees at 90-degree angles from the central point. Oh, hey, Tommy, look. It's time for the end of the show. So I had a project that I was involved with when I was out trying to develop the radiant windows. And this is a house that's here in Genesee, Colorado. If you've ever been up Interstate 70, you may have seen it before. It's just up in the foothills. And this house is called the Sculptured House. It was started in 1960 by a guy named Charles Eatherton. Charles Eatherton is the same architect that did the Chiefs Stadium in Kansas City. He liked round things for some reason. There's banks around here that look like a balloon that he also did them too. This essentially is it's a very interesting building. The guy was a structural engineer as well as an architect. And a friend of my brother's bought this house. This house has had a long, interesting history. And he essentially it went into foreclosure. And it was offered at $1.5 million. That was their minimum asking price. And so Larry went in and he bid on this thing $1,500,001, and he got the house. He won the bid and sunk an additional $3 million into the house. It was in that bad a shape, and hired me to go in and basically supervise all of the retrofit of the insulation into the structure itself. This is an 18-inch thick concrete structure, but it's two different surfaces. You've got an inner surface and an outer surface. So we drilled holes through this whole thing, and there was between 18 and 24 inches of space between the inner and the outer shell that we ended up filling with cellulose insulation. And then we also installed radiant windows in the section here. Originally, when Charles Deaton built this, he had this like rotary, guess you could call it like a record player that was half glass, and you could be sitting here and you push a button and it would turn 180 degrees, and all of a sudden you're sitting outside. And if you push the button again, then it would turn another 180 degrees and you were back inside. Well, all of the seals around this failed, and it really didn't work all that well anyway. So the owner of the place, there was a small radiant panel that was around the interior here, and it was on its own zone, and it ran continuously, and it was never comfortable. As you stood in the middle of this glass, you could feel the heat of your body going out to the glass, and there was just no way to keep it comfortable. So we did put radiant windows into this spot, and it works fantastic. You could stand there naked and not feel anything from the windows at all. So this is the exterior view from the backside. This was his bedroom. This was a small porthole. Charles was kind of a paranoid fellow, and he always wanted to see who was driving up to his house. And so basically he had this small porthole where he could look outside and see who was coming. This is an interesting window that's in the bedroom. This is another interesting window that's in the bathroom. And then this is a spiral staircase that actually goes down for 2 more stories beneath here. This is the roof of an additional structure that was added, I believe, in 1980, 1990, somewhere around there. And the guy that bought it ended up doing a significant amount of additional excavation in order to make that room larger so that we could incorporate the physical plant that we had to put into it. It originally had 3 boilers in 3 different locations, and he didn't like that. He said, I want everything in the same mechanical room. So this is what we ended up with. This is essentially 2 Lochinvar boilers. It's set up as a primary secondary distribution system. It does snow melt in the apron in front of his 3-car garage. It does some steel panel radiators. It does some radiant floor heating system. And then there is one large convector coil that is tied to a forced air distribution system. And basically this is the way that we set it up. And one of the problems that we ran into was that we could not penetrate the roof. We could not go up. I mean, this is all literally underground. In fact, this rock that's right here is at the base of the tower that supports the whole house. And so he had to be careful how far he went into that. But here you can see, this is the long run of our combustion air and our exhaust vents that take off and go down this hall, 100 foot. We push these boilers to the limit for their maximum allowable vent lengths. And one of the problems that we had to deal with was the coefficients of expansion of plastic tubing. PVC has a coefficient of expansion of 1.1 inch per 100 foot length per 10 degree Fahrenheit length. So 100 foot of length changing from 70 degree ambient to 140 degrees Fahrenheit is going to grow 7.7 inches. What are you going to do with all that growth? You got to control it. So I explained this to Larry. Larry is a commercial electrical contractor. They do highway lighting. They do the overhead signs, you know, caution rocks and animals on the highway. They do tunnel lighting. They do a lot of different stuff. And they also do a lot of bridges. And he said, you know, he says, we've got these telescoping fittings that we use for our bridges to compensate for the thermal expansion and contraction of the bridge. I'm like, perfect. That'll work. Had 3 O-rings on the inside of it. But the key with any expansion joint is you have to control the direction of growth, right? So right here, you will see that we've got unistrut clamps that are literally tied to the actual tubing itself. We're locked there. But these other ends, as you look down here, we've got pieces of 4-inch PVC that are in a PVC carrier with a 3-inch PVC pipe going through there. Those are glides. That basically allows that tubing to expand and contract through those carriers without being bound up and creating any problems from the standpoint of sending the growth in another direction. So essentially what we have is 3 different expansion joints on the system as a whole. And this is kind of a long shot. He actually turned this whole hallway here into a bowling alley. And Tom's got a video that we're going to show you at the end here that you can actually see what they ended up doing with that. But essentially, these expansion joints, we had to set them up in such a position that for the combustion air, that they were elongated because we knew that they were going to contract. As we bring in inside air out, that tubing is going to contract. And when it contracts, it basically is going to pull itself out. Whereas the combustion exhaust is going to expand. So those have to be set so that they have room to be able to expand. So you can see that we've got glides set up here, and on the far ends of the system, we've got it locked. So basically we're sending the growth and the expansion and contraction potential into these joints. And as a part of this, I required him to put a water sensor on the floor below these so that if they ever started leaking condensation, that we would be aware that we had a seal failure, which not only is going to lose condensation, it could also lose flue gases.
So I got a quick question. Are those just the common electrical expansion joints like you find at a home
Yes, they are.
parts store? Okay.
Yep.
Hey, Mark,
Yes.
but explain the code thing too, please, while we're here.
Yeah. The code. The building authorities will not allow you to put anything like this in unless it has been tested and certified. Well, nobody had ever done anything like this before. I mean, the CPVC is well capable of withstanding the temperatures that we're going to see. I don't know if I can show you this picture, but I can't get a really good angle on it. Well, kind of can. There was a section right behind this reverse indirect storage tank that the wall kind of curved, and he actually ended up bringing his son up here with a PVC heater, and we put sections of PVC pipe in there and got it almost to the point where it was ready to collapse. It was so warm, and bent them to conform to that oddball section of the wall where it wasn't. Well, you can see it here on the floor. You can see how that floor changes right here in this angle. We had to bend this PVC into there because otherwise it would have been sticking way out away from the wall. And basically, anytime that you put any kind of a device like on this, they want to see an approval. They want to see a UL rating on it. They want to see an AGA rating on it. They want to see some kind of a rating certification on it. Well, this had never been done before. And to try to go through that process is a very expensive process. I should point out that Lochinvar provided the boilers on this job. They actually donated the boilers to us because they knew that this is going to be a high profile project, that it was going to be, if you go to Home and Gardens, they've got this house on there. There's numerous different television shows that have been filmed in this house. And the consumer, Larry, considers himself an industrial artist. And so you can see these colored conduits that he's got up here. They really weren't necessary. This is what they do in hospitals and commercial settings. He did it from the standpoint of aesthetics. He provided this chrome plated diamond backing. He had his employees come up and polish all of this copper tubing. And I'm like, we should really insulate this. No, I want to see the copper. He polished it. He
So what's
varnished
that
it.
room temp, about 100?
No, it's really not that bad. And what you can't see is if I wish that I'd gotten pictures, if you turn 180 degrees from this physical plant, he's got 4 large screen TVs mounted on the wall with a large round chair in the middle of it, like the conning tower of the USS Enterprise. And I mean, this guy is just so fantastic in his thinking and the different things that he does, and everything is art. This is his favorite piece of art. Everybody that he brings into the house, the first place he brings them to is the boiler room. I got to show you this boiler room. And he ended up hiring an artist that painted gold veins into this rock and sealed the whole thing. And he's got colored lights that basically highlight I mean, how many mechanical rooms have you ever seen that had this kind of a feature? It's like the highlight of the home. I mean, it's in fact, Tom's got a video, and that you can see him saying, this is my best piece of art. So the certification on these fittings was virtually impossible to do. And as a favor to Lochinvar from having provided us with the boilers, we allowed them to come up there for an executive board meeting. And they saw these PVC joints and they went, holy crap. And I'm thinking, oh God, they're, worried about their appliance being connected to these. And he said, we've been looking for a solution to this problem forever. And he said, I think we just found it. So I think they're in the process of trying to get these things tested and certified so that they can start offering them as a means of being able to control the expansion. I mean, it's going to happen. You have to control it. If you don't control it, it's going to rip itself off the wall. It's going to rip fittings in two. It gets ugly. We see all of the net results of what happened. But this is an interesting solution that Larry came up with. I mean,
What's at the other end of those? Like, could they have just let them go straight out an outside wall, or?
No.
Probably got more 90s than at the other end?
It goes all the way down that hallway and it turns, it goes up, goes up to the deck. And then he has another piece of art up on the roof that basically hides the vent terminations. I tried to talk him into a dragon with the vent terminations coming out of the mouth.
Yeah, it's a low steam.
And he may very well do that someday. I mean, Larry's that kind of a guy. It's like he gets a wild hair, he'll grab a CNC cutter and go out and make himself some dragons so that, you know, you can have dragons with steam coming out of the mouth or whatever. But yeah, he's quite the interesting fellow. You'll see pictures of him when Tom gets into the actual video itself. So I'm done. Tom, thank you very much for the opportunity to share my 45 years worth of experience with your members. Feel free to ask any questions that you may have. And if your questions pop up at about 2 o'clock in the morning, like mine do, there's my contact information. I hope you recorded this, Tom.
Indeed.
Good. Then you've got a good record of it. So if you guys want to take a picture of this screenshot here, that's my cell phone. If you get into some kind of a jam and can't figure it out, feel free to give me a call. I'll be glad to see if I can help you.
Mark, what's your royalties on watching this again?
We'll work for beer.
Okay, sounds good. All right, I'm gonna see if I can get that video up.
Do you need me to go offline?
I don't know. I haven't done this before. I'm gonna try it now.
You know what I could probably do is bring it up myself. I just found it online. Hang
Okay,
on.
that'll work.
Nope, gotta leave Zoom up. We need,
Thanks for taking time out of your workday for this too, Mark.
well, I'm thankful I have a very understanding boss. Let's see, that was Sleeper House video.
Yeah, I think I sent you that clip in the email, didn't I?
Was it this one, CBS, was it not? Yeah, it was. 2, 1, 0. Yeah.
What's room like?
That's where we're at.
That's where we are right now.
Oh,
Yeah, Area 51 HVAC. We started in the cave at Groom Lake.
oh,
How many years ago was that, Mark? 97?
About 10 years ago.
Feels
The
like,
old guys will get that.
it feels like it, doesn't it? Yeah, Area 51 was the very first HVAC training website on the internet. The Wall, Dan Holohan's The Wall. When was that first up, Mark? 96?
Hang on a second.
Okay.
Here's this bowling alley.
Yeah, we're not seeing it in your screen right now, except for
Oh, you're not?
No, we're seeing lock and bar parts.
Oh,
how many water systems?
Let me see if I did something to you here. Nope.
huh. Says I'm sharing my screen.
I'm just seeing lock and bar parts.
Maybe it's on their screens, you dual screen.
Well, it must not be allowing me to share.
Okay.
Yep.
We're back now.
Yeah. The only thing that would allow me to share is the PowerPoint.
Okay.
Stop this.
Let me see if I can.
There, shut that off. You want to see if you can bring it up, Tom?
I can try.
I'll stop sharing.
Is that you on the bottom left, Tom?
I don't know. We'll see.
Yeah, it is. It's great.
Can you see ours, Mark?
Yes, I can.
Okay.
The mother. She looks like 7 minutes from there. So the fan's not running right now. So what we'll do, it's like right over. So we kind of leave the Brian comes up with what's going on. Get a little back lower.
This pneumatic fundamentals video.
It's this one, isn't it, Mark?
Yeah, second one down.
Okay, guys, here's the house. After the ads.
Smiles event where new patients get a fully examined set of X. Raised with no obligation, no insurance, no worries. It's free. Plus,
Well, if you've lived in Colorado a while, you're probably recognizing this home right here. It overlooks I-70 in Genesee and became known as the Sleeper House after being featured in that Woody Allen movie back in the 1970s. Tonight, our Jamie Leary shows us its owners are coming together to make sure the house is energy efficient and also preserved for future generations.
To say that this home has seen changes would be an understatement. The one thing that hasn't changed is its iconic shape. And with the vision of the current owner, every change going forward will be to make sure that it stays preserved. Larry Winkler keeps a scrapbook.
They did the movie Sleeper.
Many tried to make this home.
18 years later, Larry Pogill bought the property, designed the addition for the house, never built it.
The Winklers bought it 8 years ago at an auction. Their bid of 1.5 million was the only one.
We both looked at each other and said, oh my gosh, what did we just do?
It needed a lot of work.
We had a varmint thing going on. We had a snow coming in the house.
The shell alone required over 9,500 pounds of insulation.
The house actually became a lot warmer.
Larry also sealed doors and changed windows.
The whole time, all this glass used to roll around.
Not the best for retaining heat. An easy fix compared to the latest project. A new utility room.
We needed to really figure out how to get the utilities from one part of the house to the other part.
Which naturally called for a bowling alley.
There you go. That's kind of got a little curve going too. Oh no!
The rest of the home looks much like it did in the 60s. From the handmade staircase.
They're a little tougher to navigate in the middle of the night.
To the bedrooms.
You can see how it projects out. It actually cantilevers out 42 feet. This one, you know, it is a historical landmark. It needs to stay just like this. And it needs to, so to speak, it needs to represent.
For Larry?
The work is never done. As long as we have it, it's going to be in great shape.
In Jefferson County, Jamie Leary covering Colorado First.
Cool. Any questions?
Guys, Mark asked any questions?
Did you have a question?
Mark,
Yes.
thank you very much, sir.
You're quite welcome.
Appreciate it.
Thank you. I'll continue paying it forward and use hydronics as much as you possibly can. It's the most efficient heat transfer method in the world. And I've been saying in the 45 years that I've been doing this and teaching, I can foresee a day, one of these days, that it is the only method allowed. Unfortunately, the VRF people popped up on the radar, but I still believe firmly that hydronics is the most efficient system in the world. It employs 17 people in our company. This company has been in business for over 30 years. I've been doing it for 45 myself. I'm ready to retire in a couple of years, but I will probably still be involved from the standpoint of promoting and educating and making sure that it's done right. So thank you, Tom. Thank you, folks, for attending, and have a good evening.
Take care, Mark. Thanks again.
Take care.
Yeah.